Hello everyone. Welcome to our talk, One Engine to Foster More, Generic Language Processor Testing with Semantic Validation. Language processors translate programs written in high-level languages to low-level machine code. We use lots of them every day. For example, a browser contains processors of JavaScript, HTML, etc. Language processors should be correct. Otherwise, even correct source programs will be translated into malfunctional codes, which might lead to incorrect functionalities and even security holes. Therefore, fuzzing has been widely applied to improve the correctness of language processors. However, fuzzing language processors is hard, because to reach the deep logic, the generated input should be correct in syntax and semantics. Otherwise, a syntax error will cause a payout during the syntax parsing at the front end. And a semantic error will cause a payout during semantic actions at the back end. This puts us in a dilemma. Nowadays, we have over 770 real-world programming languages. Each of them has unique features. Generic fuzzers can easily apply to different languages, but they cannot generate high-quality inputs. Specialized fuzzers are effective for one language, but they require huge development effort to adopt on new languages. For example, given the seed input, generic fuzzers can only adopt simple mutations such as preflip, and the syntax correctness is not guaranteed. We can add the support of grammar, and the fuzzers can generate syntactically correct test cases, but the semantic correctness is still not guaranteed. We can further add the support of semantics, but after that, the fuzzers will not be generic anymore. So the question is, can we achieve both? To find the answers, we manually check 1,500 invalid inputs generated by existing language fuzzers and find that their errors actually follow some pattern. Among these inputs, syntax errors are few, because advanced fuzzers can utilize the grammar to help input generations. Most of them are semantic errors. The common root cause is that they use the definition of wrong types and scopes. For example, at line 2, we are assigning a string to a variable of type integer, so the type mismatches. At line 3, both A and B are integer types, but B's scope starts from line 4, so the scope is wrong. If we can avoid all these errors, the language correctness of the generated input will be greatly improved. Therefore, we propose Polyglot, a generic and effective fuzzing framework, which focuses on reducing the common semantic errors. It is generic because it can easily apply to different programming languages. It is effective because it can generate high-quality inputs. Polyglot achieves its goals by 3 steps. First, the front-end generation generates an IR translator to convert the source program into an IR program. Next, the constraint mutation mutates the IR program to get new variants. Then, the semantic validation fixes the semantic errors in the programs. Last, we convert the programs back to a source program and feed it into the fuzzing engine to find bugs. Now let's take a deeper look at how these steps work. The goal of front-end generation is to translate language-specific source programs into language-agnostic IR programs. We propose an IR that has syntax types and semantic properties. The syntax types represent the syntactic structure of the source code, and the semantic properties carry information about the definitions, scopes, and types. These properties are predefined by us and focuses on handle the common language features. For example, an IR with property function def means the IR refers to a function definition. To make this work, users should provide the BNF grammars and the semantic annotations of the language. Here's an example. On the left is the BNF grammar for a C function definition, and on the right is the related semantic annotations. These annotations tells which symbol in the BNF grammar has semantic properties. With this, when a source program is translated into the IR program, the translator will automatically assign those properties to the corresponding IR. For example, we know that a function body in C program will create a new scope. So in the annotations, we add the property new scope for function body. And when the function body in the source program is translated into the IR, which is IR7, those properties in the semantic annotation will automatically assign to IR7. After the translations, we can now base our mutations and analysis on the uniform IR regardless of the underlying source language. For better demonstration, we will still use source program in our example. Next is the constraint mutation, whose goal is to preserve the correctness of the unmodified part of the programs. It has two strategies. First is the type-based mutation, which can preserve the syntax correctness of the whole program. What do? We modify IRs with those of the same syntactic types. For example, we can replace A less than 0 with an IR B greater than 1, because they are both of type expressions. And after the mutations, we can see that the syntactic correctness of the whole program is still preserved. Next is the local mutation, which can preserve the semantic correctness of the unmutated part. It requires us to apply mutation only on IRs with local effect, which include IRs that don't contain new definitions or IRs that create a new scope. For example, at line 1, we define a new variable A, and line 2 use it. At line 4, we define a variable D, but line 3 to 6 as a whole is a block and create a new scope. Therefore, we cannot modify line 1 because this will invalidate line 2. But we can replace line 3 to 6 as a whole. And after that, line 1 and 2 will not be affected. After the mutation, the only thing wrong is the semantic errors in the mutated part. Therefore, our semantic validation builds symbol tables with the information of scopes and types carried by the IR, and then generate expressions to replace the invalid use of variables. Let's continue with our mutated example. W and S and Y are not defined in the current program. For better demonstration, we replace them with a special string fixme. Let's go through an example. Suppose this is the code from a function body. Let's build the symbol tables for it. Each program has a global scope, but this is unrelated to us right now, so let's skip that. Next is the function body scope, which cover line 1 to 6. And the symbol tables contains the names, types, and order ID of every definition within the scope. The order ID is the statement order in the source program, which can tell us what variables has been defined at a given location. Next is the if statement body scope, which cover line 3 to 6. After we build the symbol tables, we can find the available variables for each fixme location. For line 4, we first check its most inner scope, which is the if statement body scope. The definition K has order ID 4, which is not less than 4, so it's not available yet. And let's go up. The order ID of A is 1. It is less than 4, so it has been defined at line 4. Similarly, we can find that both K and A are available at line 5. After that, we can generate expressions with these variables to replace the fixed me. For line 4, we generate A multiply A to replace the fixed me. Similarly, for line 5, we generate K and A to replace them. After the validations, the programs become semantically correct, and we can use it for fuzzing. Our result shows the effectiveness of Polyglot. We successfully find 173 bugs in 21 processors of 9 programming languages. We choose the tested programming languages based on their popularity and domains. We cover compiled languages, interpreted languages, and domain-specific languages. We have 18 CVEs for our bugs. Some of them can lead to code execution. We also evaluate the fuzzing performance on 4 targets in 24 hours. The compare metrics include the number of unique bugs, the language correctness, and the code coverage. We compare Polyglot with 6 other fuzzers, which include Polyglot syntax, which is Polyglot without semantic validation, the baseline AFL, the hybrid fuzzer QSIM, the generic language fuzzers Nautilus, and the language-specific fuzzers Die and Seesmith. For the number of unique bugs, Polyglot finds 9 bugs, while other finds at most 2 in 24 hours. And the locations of bugs found by Polyglot are in deep logic, such as optimization and code generation. For language correctness, we check the validity of every generated input and calculate their proportions. Polyglot outperforms Polyglot syntax and generic fuzzers by at least 50%, and its correctness is not very far from the language-specific fuzzers. For the code coverage, Polyglot outperforms Polyglot syntax by 23% to 51%, and this is the contribution of semantic validation. It outperforms generic fuzzers by at least 230%. Surprisingly, it also outperforms language-specific fuzzers by at least 46%. One reason is that the input generation of Polyglot is much faster. We have a deep discussion about it in our paper. Overall, Polyglot has the best performance, except for the language correctness against language-specific fuzzers. What's the limitation of Polyglot? First, the type information of dynamically typed languages cannot be determined statically. One possible solution is to collect it during dynamic execution at the cost of performance. Next, the BNF grammar is looser than the real syntax of a language. That's why the syntax correctness of our generated inputs is not perfect, even though we use the BNF grammar. One possible solution is to use machine learning to infer the real grammar. Most importantly, currently, Polyglot only focuses on types and scopes. We can support more common language features for better performance. But how many features can we add while still keeping Polyglot generic is unclear to us. We plan to investigate it in the future work. In conclusion, we propose Polyglot, a generic and effective fuzzing framework for language processors. And we find that under equal conditions, improving semantic correctness can greatly help language processor fuzzing. We have open source Polyglot. You can find it with the provided link. Thank you.